vacuum interrupters used to leak. There was a phenomenon of outgassing or internal gassing, gases being generated. In layman's language, vacuum means nothing. But as engineers, we know it's not absolutely nothing. Still, there are 10 raised to 14 molecules per cm square. In the sense, the vacuum itself does not quench the arc, but rather it builds the dielectric strength which is required to ensure that the arc does not ignite after current zero.
Hello everyone and welcome to the video. Few weeks ago I had privilege to discuss about vacuum circuit breaker with one of the industry expert, Mr. Sandeep Kulkarni, who has been in the industry for about 20 years now, and he is one of the experts on the vacuum interruption technology. We discussed on a lot of points, and this video is the consolidated version of that. So this video is packed with a lot of learning. We'll start by understanding what is the history of vacuum interruption, the working principle of a vacuum interruption. Then we'll discuss about why vacuum circuit breaker is so popularly used in the medium voltage industry, and now why it is entering also in the high voltage industry. We'll also talk about what were the challenges to scale the vacuum circuit breaker to the high voltage technology. And then lastly, we'll talk about what is the future of the current interruption. Is it going to be the vacuum interruption all across the power system? It's a video that will provide you a lot of learning. I personally learned a lot of things while we were discussing. So for sure, you will also going to learn many things from it. This is fairly a long video, so consider yourself in a comfortable time and watch it till the end so that you learn each and everything about the vacuum interruption technology directly from an expert. So a lot of learning is waiting for you. Go and enjoy the video. But before that, make sure you subscribe to the channel so that you don't miss any of the future updates of the channel. Thank you so much and enjoy the video. So hello everyone, welcome to the video. Today we have a pleasure, or rather I would say it's an honor to have Mr. Sandeep Kulkarni with us. So Sandeep sir is coming with a wealth of knowledge. He's been into the industry for more than 20 years. He worked in different departments like the testing department. He was part of the R&D team of vacuum interrupters. He headed the design and development of vacuum interrupters in India. He is also part of CGRE committee, represented India a lot of times. He has published more than 15 papers on the vacuum technology. And it's certainly an honor to have you here, sir. Welcome to the Power Panel. And I'm certainly very 100% sure that all the discussions that we are going to have today will definitely benefit all the students, all the audience of the channel. Thank you so much for being part of this panel.
Thanks, Gaurav. Thanks for having me on this power panel. It's indeed a nice name. And congratulations. This is a very nice initiative from your side, whereby you are publishing videos on various topics of electrical engineering. I love to watch your videos. I regularly do that. And definitely these videos are of immense benefit to young engineers, students, and also experienced engineers like me. I also learn quite a lot through these videos. So keep it going on, and thanks for having me in this episode.
It's an honor, sir. So thank you so much for being here. So there are a lot of things we can talk with Sandeep sir on different topics. He's one of the expert that I've known. But today we will be talking about the vacuum interruption technology that is very frequently used in the medium voltage industry. And now it is also going into the high voltage industry. So certainly it's going to be a really interesting discussion with Sandeep sir. So let us start here with the first question that I have, sir, for you is, can you please tell us about a little bit of the history of vacuum interruption, how it started?
Okay. Nice question to start with and to set the context. So if I can ask you one question before I answer this. So can you guess how old would be the vacuum interrupter technology or the vacuum interrupter as a product? How old it would be? Any guess?
So I'll just do a wild guess here. So
Yeah.
maybe more than 50 years old.
Okay. I'm glad to say that this is the centenary year
Oh.
for the demonstration of the first vacuum interrupter. So the first vacuum interrupter was in fact demonstrated way back in 1924 by Professor Sorensen in the California Institute of Technology, or Caltech as they call it, in USA. So this is 2024. So we are indeed celebrating the 100 years of the demonstration of the vacuum interrupter technology. But of course, since 1924 was the year in which a practical switch was demonstrated. So obviously the research would have started way back, maybe 20, 30 years back. And obviously the first patent actually for a vacuum switch, right now I will not call it as a vacuum interrupter, I'll call it as a vacuum switch. So the first patent for vacuum switch was filed way back in 1890. You could imagine, even
Yeah.
before 1900s. So 1890, the first patent was filed, and then on research took place, giving the birth to the first demonstration, we can call it, of the vacuum switch. That was in 1924, as I said, and that triggered a lot of research and development in many universities. And the switch, what Professor Sorensen demonstrated, was a simple glass tube evacuated and with two electrodes which were separated to create the gap and to create the interruption, or to create a switch, what we can say. It was nothing like the commercial vacuum interrupters what we see today. So after 1924, a lot of application research happened how to convert this demonstration prototype into an actual working commercial product. So a lot of research happened on the vacuum arcs, how the arc evolves, how the arc has to be interrupted or extinguished. Then how this sealing has to be done, because the vacuum has to be maintained. It's not that we keep on continuously pumping the vacuum. So obviously we pump the vacuum and then it should be a sealed for life kind of a device. So a lot of research took place on the sealing technology. And based on this efforts in the field of sealing technology and also the arc interruption studies, we got the first commercial vacuum interrupter in mid 50s, in mid 1950s, in USA those times. But even that was plagued with quite a number of problems, like sealing was still not completely mastered. Vacuum interrupters used to leak. There was a phenomenon of outgassing or internal gassing, gases being generated from the inside components of the vacuum interrupter. Then, current chopping. So there was a challenge of current chopping also. And one more problem was anticipated, which was cold welding, welding of contacts. Okay, both under cold condition and also during arcing. So there were, of course, many challenges even after we got the first commercial product in mid 1950s, and over a period of one and a half decades after that, based on a lot of developments and research, by 1965, by 1970, we can say that the vacuum interrupter was more or less stabilized as a device for current interruption in the medium voltage.
So up to
And once
52 kV we developed till
till that
1970.
time, it was 12 and 36 kV.
Okay.
Still, and when we are talking about the mid 70s, it was still 20, 12, 24, 36 kV kind of vacuum interrupters. And then by 75 or 80, we can say that vacuum interrupter was accepted and established as a product of choice for interruption of current in the medium voltage segment. There were, of course, SF6 breakers, oil circuit breakers, the MOCBs, the BOCBs, they were still there. So in those times, VCB was just starting to gain its share or starting to find its feet, what we can say, because bulk, minimum oil circuit breakers and SF6 circuit breakers were well established. So vacuum was still coming of age. But then in the next 10 years, it was kind of say no looking back for vacuum breakers. It became a
Game
product of
changer.
choice, and then the share steadily went on rising from then onwards. Yeah, so that's history, maybe from 1890s to 1980s for the vacuum interrupter and the vacuum circuit breaker.
Yeah, certainly, it's an interesting history to look back, because there was, as you mentioned clearly, oil circuit breakers were also present. There was then air blast, SF6 were taking the market on, and then in those phase, this vacuum entered. And I think now, if we look at the medium voltage, it is completely dominated by the vacuum technology. So that's
Yes.
a great insight, sir. Thanks for sharing that. So my next question to you is, now we have the SF6 technology, we had air, we had oil. How this vacuum technology differs from this, or how the vacuum interruption works, and how different it is from the currently available technology like SF6 interruption?
Okay. Again, I'll start with the question. Have you seen oil circuit breakers or SF6 circuit breaker? SF6 you might have seen.
Yeah,
Oil
SF6 I've seen. Oil only in the pictures, not in the
only in the
reality.
pictures. Okay, okay. So vacuum breaker differs quite a lot with respect to an oil or SF6 circuit breakers. I had the fortune of seeing one of the last generations of oil circuit breakers. I can say when I started my job, oil circuit breakers were more or less extinct by that time. I'm
Hmm.
talking about 2001, 2003 kind of time period. And they were already losing the ground. They had already lost the ground. They were in the last steps of being obsolete. But I had the fortune to see a few oil circuit breakers in service. So yes, vacuum circuit breakers differ quite a lot as compared to the SF6 and the oil circuit breakers. So now we talk about two words here: vacuum interrupters and vacuum circuit breakers. Whereas when we talk about SF6 or oil, we do not have a separate entity as an interrupter. The interrupter is more or less built into the breaker when we say call a vacuum, when you say an oil or an SF6 breaker. Whereas we all know for vacuum breakers, the interrupter is a separate entity, it's a separate
Separate.
brick.
Yeah,
It can be replaced more easily. So it exists independently as compared to a breaker. Whereas
true.
in SF6 or an oil, it's an integrated part or a pole of the breaker itself. So the interrupter, vacuum interrupter, is the current interruption chamber where the contacts separate, where the arc evolves, where the arc is extinguished, and as the arc is extinguished, we say that the current is interrupted. So that's why this is called as a vacuum interrupter, because the interruption of current happens inside the medium is vacuum.
Vacuum.
Yeah. So this is where the first difference starts. In SF6 or air blast breakers, there's a positive pressure of either SF6 or air. And in case of oil, there's obviously oil in the liquid form.
Hmm.
Whereas in case of a vacuum interrupter, it's actually devoid of medium. When we say vacuum, in layman's language, vacuum means nothing. But as engineers, we know it's not absolutely nothing. Still, there are 10 raised to 14 molecules per cm square. If we go by that Avogadro's number, that philosophy, still there are plenty of molecules present, even when we talk about 10 raised to minus 6 torr, which is the pressure at which generally the vacuum interrupter operates. So here, vacuum is being used as a dielectric medium more than as an interruption medium. In case of SF6 gas or oil, I'll take the example of SF6 gas because many of the today's engineers still would have seen SF6, would have learned SF6. So how current interruption happens in SF6 is the arc is bombarded with high velocity SF6 gas, and the role of SF6 gas is to, first of all, flush out all the electrons, because we know SF6 is an electronegative gas.
True.
So it absorbs or takes away all the electrons from the arc. Secondly, it cools the arc because SF6 gas has a good thermal conductivity. So it
Hmm.
cools the arc. And when we know that any medium is devoid of electrons, it becomes even more difficult for the current to exist. That is, the
Hmm.
arc to exist. And when we again cool down the arc, the conductivity of arc would decrease, the resistance would increase, and again we create a more conducive environment for arc interruption. So this is how SF6 work, and I call it as an active form of working. Whereas vacuum interrupters are more passive, in the sense the vacuum itself does not quench the arc, but rather it builds the dielectric strength which is required to ensure that the arc does not ignite after current zero. Okay, but to do that, there are certain preconditions that the temperature of the contacts should be below a certain threshold. Also, the metal vapor which is inside the vacuum interrupter should not be above a certain threshold. We call it the metal vapor density. Uh, so these two thresholds once met, that is, the temperature is below a certain threshold of the contacts, and the metal vapor density inside the interrupter is not above a certain threshold. If these thresholds are met, then there are the situation is very much conducive for creating an environment that the vacuum as a background medium ensures that the arc does not ignite after the first current zero or the second current zero. Now, how to ensure these two thresholds? So, as I said, we need to keep the contact temperature below a certain value. Now, why does the contact temperature increase? Now, I'm going in the backward direction. I'm starting from
Yeah,
current
yeah.
zero and going how the arc is generated inside. Okay.
Yeah.
So we know that any switch, for that matter, when you it's a mechanical switch. When you separate the contacts, there will be an arc, no matter how small or how tiny the arc is. Even a tube light switch at our home, if it's an inductive tube light, not today's LED tube lights, but in the olden days, there used to be inductive chokes. So there
True.
used to be a lag of current because of Lenz's law, and still the current used to persist, and we could see a tiny spark behind the switch. So current tries to exist. It tries to oppose the interruption.
Mm.
So the moment we mechanically separate the two contacts, the current does not die out at that moment. It stays. Okay, that's the very nature of the current, and that's why you and me have jobs, isn't it? If current would have died out instantly,
True,
switchgear
true.
engineers wouldn't have had any jobs.
Mm.
There wouldn't be any circuit breakers or interrupters, no Gaurav or no Sandeep required.
Correct.
Okay, jokes apart, coming to the crux of the matter. So when the pack separate, the current tries to maintain itself, and in the form of arc, and the intensity of the arc depends upon the value of current. So if it's a fault current, like say 20 ampere or 40 ampere, the intensity would be obviously much more as compared to a rated current extinction, say 1600 ampere, 2000 ampere. And this arc can exist in various forms that I will come to. But the moment the contacts are separated, an arc is formed. Initially, when the contacts are a short distance apart, the arc is spread out, more like water coming out from a shower,
Mm.
with a lot of paths. So the arc is well spread out. But after a certain threshold of the value of current, because as we know, current is sinusoidal, so it is rising, and above a certain threshold, this shower nature of the arc, what we call as a diffuse nature, it gives way to another form of arc, what we call as a constricted arc. Constricted arc is like a candle or a stick, or like a cylinder having a smaller diameter. Okay, so this constricted arc is formed after a certain threshold, and this constricted arc creates an increase in temperature of the contacts. So, as I said, we need to keep the temperature of the contacts below certain threshold. So, from where does this temperature come? This arc.
From
So,
arc.
the arc is responsible for raising the temperature of the contacts, because arc is nothing but plasma,
Mm.
high temperature plasma composed of electrons, ions, metal vapors. Okay, so it's a composition of all these, and it's extremely high temperature. It can easily vaporize, not even melt, but vaporize copper and chromium,
Mm.
which are the elements present inside the contacts. So this arc, which is now in the form of a cylinder, increases the metal temperature, which causes the evaporation of the metal
Mm.
from the contacts. And this is all happening when the current is still there. Okay, the current is still flowing, and now the current zero is approaching. Okay, and the current zero is approaching. And as we know, at current zero, there is a phenomenon of called as RRRV, rate of rise of recovery
Recovery
voltage. The moment
voltage.
we approach a current zero, there's a current zero pause, as we call.
Hmm.
It's for a very short duration of few nanoseconds, but there's a pause in the value of current.
Hmm.
And
Hmm.
the moment it happens, the rate of rise of recovery voltage kicks in. And then there's a race, the famous race between rate of rise of
Yeah.
recovery voltage and rate of rise of dielectric strength.
Dielectric strength.
The one who wins the race decides what is going to happen the next. For us, the switchgear designers or electrical engineers, we the task is to help the rate of rise of dielectric strength to win the race and not the RRRB. So
Hmm.
as to ensure that the current is interrupted at the first current zero, if not at the first, at least the second current zero. So as I said, the contacts are being heated by this arc. So we need to reduce the temperature. Okay, so there are two ways of reducing this temperature. One way is to not the arc being constricted. As I said, initially the arc is in the form of a shower with a
Hmm.
lot of parallel paths. And as we know, if there are a lot of parallel paths, the current density is lower, isn't it?
Correct. Correct.
So current is more uniformly distributed, and so is the heat. But once the arc becomes constricted, like a cylindrical, so the current density is very high because now the current is concentrated on a very small area of the contact. So why can't we keep the arc in the diffused or in the shower mode? That will be the first obvious question.
Hmm.
Yes, we can do that, and that is one of the ways to reduce the heat load or the joule input to the contact surface. And that technology is called as the axial magnetic field technology, where we apply an axially oriented magnetic field to keep the arc in the diffused mode.
Okay.
Yeah. Alternately, we allow the arc to be in the constricted mode, that is in the cylindrical mode. We accept, okay, if you want to be in the cylindrical mode, no problem. We let you be. But then we will not allow you to position yourself at any single location. We will continuously move the arc.
Hmm.
Now you imagine there's a candle and there's a flame of the candle, and if you keep your finger in that flame, obviously you'll get hurt. Your finger will sense the temperature. But if you move your finger very fast through that flame, you may not feel it.
True.
Or you would have seen people walking on the coal beds, burning coal beds. If you
Hmm.
walk
Hmm.
very fast, your feet would not feel the heat. So same philosophy we are using here. What we do is we move the arc very
Hmm.
fast. So once you move the arc fast, so it's the reverse. In that case, the candle flame is stationary. You move your finger. In this case, the contact is stationary, and we move the arc on the contact surface.
Oh.
So contact does not then feel the heat to the same extent as it would have felt if the arc would have been stationary,
Hmm.
because now different positions of the contacts are getting heated, and the speed of rotation is so fine tuned that it should not be too fast. If it's too fast, then the arc will come back at the same location in a very short time. So we will lose that advantage of not
Hmm.
letting it get overheated. If it's too slow, the arc will stay at any particular location for a very long time. So the designers of this contact design the contact in such a way that the arc rotation speed is optimal, not too slow, not too fast. And how we rotate is we apply a magnetic field, which is called as a radially oriented magnetic field. And here we go back to our college days, Fleming's left hand rule. You remember Fleming's left hand rule?
Yeah.
So what does Fleming's left hand rule tell us?
I remember it's difficult for me to.
Okay, fine. Okay. So even I don't remember the exact fingers what they point to, but we know it's a rule which tells us about the relationship between the current, the magnetic field, and the force. We
Force. Yeah.
use it for understanding the rotation of the motor. So we use the same rule here. So there's a current, okay, which is flowing in the form of an arc, and there's a contact, and we design the contact in such a way that the magnetic field which is getting generated by the flow of current is perpendicular to the flow of current.
Hmm.
So if magnetic field and current are perpendicular, then the third direction, if one is x, second is y, then the z direction would be the force
Force.
which is acting on this conductor, because we know any current carrying conductor placed in a magnetic field experiences a force. This is how the motor rotates.
True.
this is how the arc rotates. We use this principle or this phenomenon to rotate the arc. The arc is carrying the current, so it's a conductor, and the current itself creates the magnetic field through specifically designed contacts. This magnetic field interacts with the current, and what we call as the J cross B force, JB sine theta,
Mhm.
in vector terms. So that JB sine theta is the J cross B sine theta is the force which gets generated, and this force is a circumferential force which makes the arc to rotate. So the current is axial, the magnetic field is radial, and the force is circumferential. So under the influence of the circumferential force, the arc rotates. And as the arc rotates, as I said, the heat input to the contacts reduces. This ensures that the temperature is kept under check, and the generation of the metal vapor also reduces. So the two conditions which are required: reduction in the temperature of the contacts and reduction in the metal vapor. As I said
Yes.
during the start, that these are the two thresholds what we need for creating conditions which are conducive for ensuring that the RRRB does not win the race. And then the rest, the vacuum takes care, because we know vacuum is a medium which is having very less number of particles as compared to normal atmospheric pressure. And once we have less number of particles, then there's a concept called mean free path. The distance between the two collisions is increased. The mean free path is increased. So the probability of collision decreases. And
Hmm.
as the probability of collision decreases, we say that this results in a high dielectric strength of that medium. So this is how the vacuum plays a role. It creates a high dielectric strength atmosphere or a medium around the contacts, which have done their job of ensuring low threshold of contact temperature and low threshold of the metal vapor. And why the contacts have to be at a lower temperature? Metal vapor, we understand, if metal vapor is there, it will form a conducting channel, okay,
Correct.
isn't it? And then the current will easily flow through this metal vapor. But why do we also need the temperature to be at a low level? The reason is what we know as thermionic emissions. So we know that metals can emit electrons when heated.
Hmm.
So, but there is again a threshold. If the temperature is below a certain value, then this thermionic emission does not happen. So that's why we need to keep the temperature of the contacts below a certain threshold. Otherwise, even if there's no metal vapor, the superheated contacts will start emitting electrons in that case.
Hmm.
And that's why these two thresholds are met by designing the contacts. And the vacuum as a medium ensures that the RRDS wins the race against RRRB, and the current gets interrupted. So this is how, in a nutshell, a vacuum interrupter works.
Clear. I think when we say the SF6 interruption, it is because the SF6 gas takes out all the available free electrons from the interrupter part. But
Yes.
when we open the contacts in the vacuum, so since anyways there is no free electrons present, does it also helps in breaking the current?
No, the current interruption solely depends upon the contacts and also depends upon the metal vapor.
Mm-hmm.
So at that moment, till current zero, vacuum is not playing any actual role in the current interruption. The role of vacuum starts only after current zero.
Oh,
So till current zero, the entire phenomenon of generation of metal vapor is guided by the sinusoidal increase in current, and it depends upon the contact metallurgy. And also there are some surrounding elements like contact shields or vapor condensing shields. So these are the elements which play a critical role in deciding what is happening till current zero. Okay, and after current zero, then it's the role of the vacuum medium which takes over.
okay. And I think that's why you rightly mentioned in the beginning of this question that vacuum is a dielectric medium rather than it's an interrupting medium.
Yes,
I think
yes,
that's a
yes.
very interesting statement and also very important statement. And definitely, it's a very interesting technology that you explained. And the way you explained, I think it made it very simple for us to understand. At least I learned a lot of things from that question. So thank you so much for that detailed answer on how vacuum interruption works. So
Just if I
ultimately,
can add
Yeah, yeah.
here, because I talked about vacuum interrupter, but we also need to know something about the vacuum breaker, how the interrupter coordinates with the vacuum breaker, because um, not many of us would see a vacuum interrupter in field. We would see a vacuum
True.
breaker, isn't it?
Yeah.
So I'll touch upon how the vacuum interrupter interacts with a vacuum circuit breaker. So as I said, it's a mechanical separation of contacts takes place. There's a fixed contact and there's a moving contact inside a vacuum interrupter. So the moving contact is actually coupled to the mechanism of the breaker
Hmm.
through a lot of linkages, which I'll not touch upon right now. But there are a lot of linkages which through which the moving contact is connected to the breaker mechanism, and there are certain bands of opening speeds which need to be maintained to open the contacts or to move the moving contact away from the fixed contact, which ensures that the current is interrupted. That's how the breaker and the interrupter are coupled to each other. Not only the mechanism, but the breaker also provides the mechanical support or the mechanical housing to the vacuum
Good
interrupter.
interrupt.
It also provides the current carrying path, because vacuum interrupter is just a cylinder. There has to be current carrying path which connects the external world to the vacuum interrupter. So this current carrying path is also provided by the vacuum circuit breaker. So I thought I should touch upon how interrupter and breaker are related to each other.
Yeah, sure. Because that is important when we talk about medium voltage. As you mentioned, we have dedicated bottles of vacuum interruption. So how
Yes,
it is
yes.
connected, how it is interlinked, I think it's a valid point that you mentioned. Thank you for that. So ultimately, what we have to remember is in any sort of interruption, if your dielectric strength recovery rate is higher than that of the rate of rise of recovery voltage, the current interruption is possible, and
Yes.
that's how it happens in vacuum interruption also. So
Yes.
thank you, sir, for that detailed answer. I think it will solve a lot of confusion that people had in their mind. Thank you so much for that. And certainly, after hearing all of this, I'm really interested in knowing more details on this. So, if you can share us, if there are, let's say, if I want to know more about this, there are some conferences that happens or some events related to the vacuum interruption. Can I attend this, or how to go into that? Any details you have on that?
Sure, Gaurav, and I'm happy that this discussion has kindled in you to look for more literature on vacuum interrupters, and I hope the listeners also would be interested to know more about this technology. So yes, there are quite a lot of books which you can refer to on vacuum interrupters, and there are conferences happening world over related to this field. If we talk about IEEE, then there's a dedicated transactions called as IEEE Transactions on Plasma Science. Okay, many of the papers which appear in this journal are related to current interruption in vacuum. So then there is IEEE transactions on dielectric and insulation system, DEIS, what we call it.
Mhm.
So that is more towards the insulation performance of the vacuum as compared to the interruption performance. So these two basic IEEE journals can give you a lot of knowledge on current interruption in vacuum, and also how vacuum as an insulator or as a dielectric is playing a role in this current interruption. And talking about conferences, one conference which comes to my mind at the top of my mind, because it's a premier conference in this field. It's called ISDEIV. Okay, I'll give this full form. ISDEIV stands for International Symposium on Discharges and Electrical Insulation in Vacuum. Okay, I'll repeat it. ISDEIV, International Symposium on Discharges and Electrical Insulation in Vacuum. So it deals with a wide range of subjects. As the title suggests, discharges in vacuum and insulation in vacuum. But this conference is not confined to vacuum interrupters alone, because there are a lot of applications of discharges and electrical insulation in vacuum. X-ray tubes are a perfect example of where vacuum is used as an insulating medium. Particle accelerators, plasma research, fusion, space research. So there are a lot of applications, thin film depositions, where we have vacuum, where we have discharges, and where we have insulation. But since we are talking about vacuum interrupters as a subject today, I would definitely say that this is a premier conference for researchers or industry experts or students who would like to know more upon the vacuum interrupter as a subject. So you can Google it, ISDIV. You can get the link to this conference, and it happens every 2 years. It started way back in 1962 or 64 in USA, and after that, it has been happening every 2 years in a different country. In 2014, I was fortunate enough to be part of a committee which organized this conference in India. That was the first time this conference was organized in India. We had it in Mumbai. I personally started attending this conference since 2008 when it was held in Romania, and since then I have been attending almost all the editions of this. And the last one was in Okinawa, Japan, where I attended. And next one is going to be in China in 2025. So the call for papers is still open. So if anyone of you are interested to publish the paper, the abstract submission date I think is around end of January, and the conference would be happening in September in Sichuan University in China. So students or researchers who would like to submit the papers or contribute to this conference or even attend this conference, you can take a note of that. And Gaurav, I'm sure you'll definitely share in the
Yeah.
video the link to this presentation. So you can take advantage of that. And definitely, if this talk has kindled in you some interest in the field of vacuum interrupters or how interruption happens in vacuum, do not miss to attend this conference. And for any queries regarding this conference, I'm open to answer those queries because I am on the permanent committee of this conference. So there's a permanent committee which governs this conference, and glad to share that I'm one of the members in the permanent committee. So I'll be happy to answer any queries or support you in terms of publishing the papers or attending the conference. So hope it answers your question, Gaurav.
Yeah, definitely. I'm looking forward for this conference that is soon going to happen in 2025 in China. And definitely, as you mentioned, we'll put links for those down in the description so you can go and check it out. How is this conference? What are the details of that? Will be available. And if you want to present any sort of paper or anything, we'll also be providing an email ID in the description where you can reach out for some of the queries. And sir is there for us to help because he is one of the permanent committee member of that. And I think that's a golden opportunity for you also to interact with him. So definitely take the full advantage of this opportunity.
Thanks, Gaurav.
Why the medium voltage industry is, I think, almost dominated by the vacuum interruption, and why not the SF6? Or rather, what are some of the benefits that we get by using vacuum interruption rather than the SF6 interruption?
Okay. So slightly I'll go back to the history because when I said that vacuum interrupters started appearing on the scene in the 70s, 80s, or rather I should say vacuum breakers started appearing on the scene, and then they took baby steps towards establishing themselves. And by 90s, they were the norm. Vacuum breakers became the norm for medium voltage current interruption. But SF6 breakers and oil breakers still existed in those times, and the share was quite equal. But by 2000, it was more or less complete domination of the vacuum breakers, and there are multiple factors to that. Let's talk about why oil went into obsolescence as compared to vacuum. So when we say oil, it's a fluid. There are issues related to handling of the oil. Then when the arcing happens, there are byproducts of the oil. It needs to be filtered. Then there are many EHS issues regarding the disposal of oil. Also, the life of the interruption life of an oil circuit breaker is also limited.
Yes.
So there were a number of factors which led to the obsolescence of the oil circuit breakers. So then the two obvious candidates which were left in the fray were SF6 and vacuum circuit breakers. SF6 is, I should say, kind of a workhorse. It has a lot of advantages, and it's a very reliable technology. SF6, as we know, is an electronegative gas. So the most important condition which is required for interruption is that of electronegativity. It takes away all the electrons. It has good thermal conductivity. It has good dielectric strength, almost 3 times that of air at the same pressure. So obviously, it is an ideal candidate for a current interruption. So that's why it existed, and it is still existing in high voltage domains. But again, there are some disadvantages of SF6 as compared to vacuum. The energy required for an SF6 breaker is obviously higher than a vacuum breaker because the stroke is higher.
Mm.
Now, if I correctly mention, for a vacuum breaker of 12 kV rating, the contact stroke is not more than 6 to 8 mm. Whereas if you talk the same for an SF6 breaker, I guess it will be about 30 mm, the contact stroke for the SF6 breaker of the same rating.
So
So
almost three
obviously,
times.
almost three times. Yes, yes, almost three times. So obviously, the mechanism needs to be having more energy to create that much of opening. I think the opening speed is also more required for for SF6 breakers as compared to vacuum. So obviously, the energy content of the mechanism is higher.
Mm.
Then again, SF6 gas itself became a bit of a concern in the mid 90s, started becoming a bit of a concern because in 1996 Kyoto Protocol, it was declared as one of the greenhouse gases. So this meeting happened in Japan. Nowadays, I think we call it the COP meeting. It was called the Kyoto Protocol in 1996, wherein SF6 was identified for the first time as a greenhouse gas. And not just identified, but the global warming potential assigned to SF6 was somewhere between 23,000 to 25,000 times of that of
Huge.
CO2. So it's huge. So obviously, that created a mindset about SF6 being not so environment friendly. And obviously, since there was an alternative available in terms of vacuum breaker, which was serving the purpose, so vacuum breakers gained traction as compared to SF6 breakers. The handling of SF6 gas is also a challenge. There are byproducts generated after arcing. So the disposal of those byproducts is a challenge. The life of vacuum breakers is certainly much more as compared to an SF6 breaker. So that obviously now is definitely an advantage for a utility, which is looking to what we call as the time between two maintenance operations or time
Mm.
between two replacement requirements. So vacuum breakers obviously gives a much greater life in terms of the number of current interruptions at the same level as compared to an SF6 breakers without requiring any maintenance. So because of these advantages of having a lower stroke, a mechanism requiring lower energy, more environment friendly, and one of the most important advantages I would say is the adaptability or the replaceability. If a vacuum interrupter goes bad, say a vacuum loss happens or the contact welds, you rack out a breaker, you replace the vacuum interrupter, you check, you do the preventive maintenance checks or pre-commissioning checks, you rack in a breaker, it's ready. It's not the same in case of SF6 breakers, I suppose. It's much more complicated to replace one pool of SF6 breaker. You need to drain out the gas, and that too in a manner which is environment friendly. You need to take care of the byproducts which would have gathered due to the arcing. Again, fill the SF6 gas, do the pre-commissioning checks, and then again it's ready for the next round of operations. So obviously there are many advantages of the vacuum breaker technology. I might have missed out some things, but these are the main things which come at the top of my mind. Why vacuum breakers are now dominating, and now it's a complete dominance. The oil breakers do not exist. SF6 breakers only, like ppm level, they would be existing in the medium voltage, and rest is completely dominated by vacuum breakers.
Yeah, yeah, true. And you touched upon a point where the contact difference, there is a huge gap. So
Yeah.
vacuum, when we say a contact difference and the contact difference between the SF6 breaker, it's almost three times difference.
Yes, yes, yes.
So will that also affect the size of the circuit breaker?
Yes, definitely. So as I said, for a 12 kV vacuum breaker, the contact gap is 6 to 8. SF6 maybe 25, 30. I am not sure exact figure, but it's could be of
Both,
that
yeah.
order. But certainly it's a difference, and that results or that translates into the dimensions of the total pole. Yeah,
Mm.
so obviously the total pole since it needs a bigger gap, will be bigger in SF6. The mechanism will be bigger. And why 6 to 8 mm is okay for vacuum interrupters or vacuum breakers? It's because of vacuum. So in the last question, I touched upon how vacuum is playing as a role, more of an insulating medium. Okay, so even a gap of 6 to 8 mm can withstand the required impulse voltages, because these gaps are designed from the impulse voltage withstand point of view. So for a 12 kV, the rated impulse withstand voltage is 75 kV. For 36 kV, it is 170 kV. So these gaps are designed, or the gaps are defined or constrained from this impulse voltage withstand performance. And since vacuum being an excellent insulating or dielectric medium, even such a low gap, with such a low gap, it can withstand with impulse voltages as high as say 75 kV for a 6 to 8 mm gap. In fact, 6 to 8 mm gap can withstand even higher than that. But I'm saying 75 kV because it's the rated voltage for 12 kV range. So yes, here the key player is the vacuum as an insulation medium, which is ensuring that we have a low contact gap.
Yeah, correct. I think, and after listening all these advantages, I'm 100% sure why the medium voltage industry is completely dominated by the vacuum. I think that's the best choice that we have, considering the available options that we have. Vacuum
Yes.
is the best choice, and I believe I will not be surprised if vacuum technology soon also dominates the high voltage market. So currently, it is dominated by the SF6 interruption. But recently in the CGRE conference, one of the manufacturer also unveiled a 400 kV vacuum interrupter. So certainly this vacuum technology is also entering into the high voltage world. So
Yeah.
anything that you would like to talk upon that?
Yeah, certainly. As you rightly said, the vacuum interrupters or vacuum interruption technology is making its foray into the world of transmission class breakers, because these 12 and 36 kV breakers, we call them as a distribution class. 72 kV onwards are the transmission class. And certainly, yes, there is a lot of traction for vacuum breakers to make push in the vacuum in high voltage domain also. I'll go back a bit in history. As I said, the vacuum interrupters were developed somewhere around 60s, 70s, the commercial products. And obviously, 12 kV was developed, 24 was developed, 36 was developed. And we would not be surprised that to know that even 72 kV vacuum interrupter was developed in 1980s itself. Okay, so it was not new. So there are literatures available. There are, in fact, photographs of prototypes available, which inform us that even in the 1980s, 72 kV vacuum interrupter was available. Even before that, I had read in one of the literatures that in 1970s or late 60s, there was a vacuum switch which had a rating of 168 kV or 150 kV. I don't remember the exact rating, and it had 8 interrupters in series. So a vacuum switch operating at transient voltage is not new. It's like electric vehicle is not new. We know there were prototypes or there were examples of electric vehicles or EVs way back in 1930s or 40s. So similarly, a vacuum switch or a vacuum breaker at transmission voltages is not new. Technology was there, prototypes were there, working prototypes were there, which worked on the field. But those times, the alternatives were much more attractive. SF6 breaker was there. Like I said, it was a workhorse, reliable, um, and accessible. And that time we did not know about the environmental impacts of SF6. It was able to handle say 40 kiloampere, 50 kiloampere. You asked for it and it delivered. So that technology was available, that technology was mature, and that's why in those decades the vacuum breaker technology at transmission class may not have gained that much traction, and there were some challenges in industrialization of big size vacuum interrupters, because when you say 72 kV or 145 kV or 245 kV vacuum interrupters, they are quite large in size. And one reason is the dielectric strength of vacuum medium does not linearly increase with the gap. So if you say you can withstand a certain voltage at 6 to 8 mm, X voltage, you will not be able to withstand 2x voltage if you double the gap. It will be slightly less. And the curve becomes quite asymptotic as you go higher in the gap. So when you want to realize higher voltage interrupters, the gaps increase disproportionately. Not only the gap between the two contacts, but there are some internal floating shields. Okay, so between the floating shields also the gap needs to be accordingly adjusted. And those increase disproportionately with the voltage, and so the size of the vacuum interrupter becomes quite big. And to have a sealed for life device in such a big size, it was challenge in those times. I'm talking about 90s or 2000s. So it was definitely challenging in terms of brazing technology, the size of the furnaces, and it was not economically viable or economically attractive because SF6 breakers were there. So people or utilities may not be ready to pay the premium for a vacuum breaker as they may be ready to pay today because of all these concerns related to SF6 being a greenhouse gas. So yes, my point is the technology was there, products were there even in the last century, like in 90s, 2000s of the last century. And what has changed now is SF6 being concerned as the greenhouse gas. So there's a big push to reduce the use of SF6 in our products. And that big push means we need to find alternatives to SF6. So there are two paths. One, we find an alternate gas. A lot of research is happening, as you know, on that front also to find an alternate gas. And second alternative is to use vacuum interrupter as the current interruption medium rather than a gas. So since early 2000s, a lot of research is being done. In fact, in Japan, vacuum breakers at 84 kV or maybe even 145 kV were used in the late 90s or 2000 and early 2000s also. And I was part of a SIGRE working group called A327, which looked specifically at this aspect of application of high voltage vacuum circuit breakers. So we looked at different aspects about what are the challenges in manufacturing of the breakers, challenging in the design, challenges with respect to the interaction with the network, because the phenomenon happening inside a vacuum breaker is different what happens inside a SF6 breaker. So even the interaction with the network will be different. So there was a lot of study with respect to that. But in the last decade, I can say, yes, a lot of prototypes, not only prototypes, but applications we can see on the site for definitely 72 kV, but even 145 kV in Europe, Japan, China, USA. There are examples of 145 kV vacuum breakers serving on the site. And as you said in one of the conferences, you saw a paper or a demonstration of a 400 kV. I definitely have seen a 245 kV prototype in the literature. So if definitely if 400 is there, then it's definitely a big news. So this is where vacuum interrupter technology stands today in the field of high voltage breakers, and that's going to be the future. So as I said, either an alternate gas or vacuum interrupters utilized at say 245, 400, 765 looks quite difficult. Maybe we will need to connect multiple interrupters in
Yeah.
series to achieve 765 kV. But we don't know where the technology takes us in the next decade. But it will be an interesting decade to see how the vacuum interrupter technology progresses.
True, true. I think you mentioned now, since till a certain voltage limit, like 52 kV, the ban on SF6 is coming soon. There are already regulations in place. And maybe in coming years, they will also ban the SF6 from transmission products.
Yeah.
That is going to happen. So, and that is also the reason why now all the manufacturers are looking for alternative of SF6. Like you mentioned,
Yes.
vacuum could be one of the potential candidate for that. So far, you mentioned that the one challenge was the economics behind it. So definitely the vacuum technology for transmission level circuit breakers was very expensive than the available options. But apart from that, do you see any other challenges were there to extend this technology to the transmission level circuit breakers?
Yes, as I said, there were a few challenges. Like it came to more about industrialization, that is the manufacturing of big vacuum interrupters, because there are multiple vacuum joints in this. So to ensure long-term reliability of these vacuum joints was one of the challenges, but it's more or less mastered now with a lot of research and developments on the brazing technology. It is more or less mastered. People are also looking at the contact material. In medium voltage, okay, I forgot to mention the medium voltage vacuum interrupters use copper chromium as the contact material.
Mm-hmm.
Now, whether the same contact material would be suitable at HV or EHV levels, that is one problem researchers are working on. Then, as I said, the gap or the dielectric strength does not increase proportionately with the gap. So the grading of the field inside the vacuum interrupter becomes very important when we talk about HV or EHV interrupters, because the impulse withstand voltages are quite high.
Mm.
And when we go certain beyond certain voltages, we also get the switching impulse up to
Yeah.
145 kV. If I remember, it's only the lightning impulse.
Lightning
Beyond
impulse.
145 kV, there is also the switching impulse, which is
True.
more stringent as compared to the lightning impulse withstand. So the grading of the internal fields of the vacuum interrupter is one more critical
Mm.
challenge with the researchers would to be definitely working on how to solve it. And there is one phenomenon which I touched upon is the magnetic field, use of magnetic field in current interruption. So as we increase the gap, the magnetic field density or the magnetic field strength goes on reducing. And for example, for a 72 kV interrupter, the gap needed might be somewhere around 70 or 30 mm, 35 mm. I'm not sure how much. But then we also need to design the contacts accordingly such that the magnetic field is strong enough even at such an increased gap. If the magnetic field is not strong enough, the arc will again go to its constricted mode. It may not stay in the diffuse mode. So this is one challenge which the researchers definitely are looking at, and they would have definitely solved the problems. And one challenge for vacuum interrupters is the conduction of heat. In case of SF6, there's a gas which acts as the conducting medium. Through convection, it cools not only the arc but also the electrodes or during normal carrying. In case of oil, it used to be even simpler. Oil being all around, it used to cool. SF6 gas cools. In case of vacuum, it's only radiation
Mm.
which dissipates the heat, and the conduction which happens through the electrode itself. And radiation is also not that effective because we have a ceramic surrounding the electrodes which are carrying the current and which are a source of the heat. So the only remaining option is the conduction of heat through the electrodes, and which are quite long when we talk about high voltage vacuum interrupters. And we know R is equal to rho L by A. So resistance is directly proportional to the length of the conductor. So the current, as the length increases, the resistance increases. And these high voltage vacuum interrupters would be invariably rated for higher currents, 3150, 4000 amperes. So the thermal management or the management of the heat dissipation is also one of the challenges, which the may not be the interrupter designers, but definitely the breaker designers would be looking at. And one more challenge is, okay, you achieve the dielectric strength inside the vacuum interrupter using the vacuum, but what about around the interrupter? You
Yeah.
still need some insulation medium, isn't it? You cannot use SF6. If you use SF6, you are not fully solving the problem.
True.
Obviously, the first choice will be SF6, the simplest choice, very high dielectric strength to use SF6 gas around the vacuum interrupter. You get the required dielectric strength, but then you are not fully complying the requirements from the environmental point of view. So the option is using an alternate gas like air or nitrogen, but then you need to use it at much higher pressures to reach the equivalent dielectric strength of the SF6 gas. And higher pressures bring their own challenges. The enclosure in which the interrupter would be mounted would need to be accordingly reinforced or strengthened to handle that high pressure of that gas which you are going to use as an external insulation medium. Then the leakage of that gas has to be again handled. The grading of the field around the interrupter would have to be handled. So yes, there are challenges, but then since we see working prototypes at 72 and 145 kV, we would have definitely overcome these challenges to a certain extent. But yes, so as you said, these are some of the challenges which the researchers are working on,
Good.
and they would definitely continue to work on.
Sure, sure. I think true insights that you mentioned, and as I mentioned, we will not be surprised if we see, vacuum technology also dominates the high voltage market soon, because the ban is coming and it's inevitable. For sure, the SF6 will phase out because we don't have planet B. So there is a
Yes.
lot of scope that
Yes.
we have in vacuum interruption technology for high voltage and extra high voltage circuit breakers.
Yes.
So thanks for sharing all the insights, sirs. It's really helpful. And maybe now I'll ask you the last question, because of course there are a lot of things that we can learn from you, but the time is short. So one last question is, uh, from your point of view, what is the future of this vacuum interruption technology? And what are some of the suggestions that you will give to young engineers who would like to, go inside the vacuum research, or the people who would like to switch their career into the vacuum interruption technology? What are some of the tips or suggestions that you would like to share with them?
Okay. The first suggestion would be welcome. Come on board. I'll be
For sure.
happy uh, to have young engineers working in a field which is so close to my heart. That is vacuum interrupters and interruption in vacuum. And yes, the future is bright for the technology and also for the engineers who would be working in this field. As you said that in the coming decades, vacuum interrupters or vacuum breakers are going to dominate in the high voltage arena as well. So there would be a lot of developments taking place in this field. Vacuum breakers up to say 400 kV, even 765 kV would be developed. Vacuum breakers with higher fault current ratings would be developed, because higher fault current rating is also a trend which is happening, because
Mm.
fault currents are generally increasing world around. Okay, as the networks grow, the fault levels grow. Okay, as the number of loads which are getting added into the system, the faults level are growing. So we need to develop devices which are suitable for interrupting higher faults current. The same substation maybe 30 years back, which was handling 25K, now has to be augmented to 40K, going to 63K, 80K. So definitely that is one aspect which we need to look at. Second aspect which we did not touch upon, but which also exciting, is generator circuit breakers.
Yeah.
Generator circuit breakers are even today dominated by, I
Vacuum.
will say, gas breakers.
Hmm.
In earlier times, it used to be air blast breakers, and nowadays it is SF6 breakers. Two reasons. Um, the fault current is very high. When we talk about generator breakers, it's upward of 80 kiloampere. It can go up to 200 kiloampere also. And secondly, the DC component is very high.
Mm.
At the output of the generator, the DC component can touch even 100% or 120%, which is typically 40% in the distribution class breakers. So the requirement of the breaker to handle the energy is exorbitantly high. uh, High fault current and high DC component. So you keep the breaker keeps on waiting for the current zero, but it appears after a very long time. Now here we are talking about milliseconds, but for us engineers who are working in this domain, even 100 milliseconds is a very long time, isn't it?
Yeah.
If a current zero does not appear at 10 milliseconds, we will be worried, definitely, isn't it? For people outside the world, 10 milliseconds is nothing, but for us, even 10 milliseconds is everything. In
Everything.
fact, I'll just take a detour. There is a club called Current Zero Club. Okay. The Current Zero Club, the people of Current Zero Club are working exclusively. What happens 200 nanosecond before current zero, 200 nanosecond after current zero. So you can imagine they have devoted their entire life to these 400 nanoseconds.
Mm.
And why I took this detour, just to tell the young engineers that even such kind of opportunities exist if you want to go deep in this field, and the rewards are also high. You get a lot of acknowledgements. You get a lot of publications, recognitions. So yes, so this coming back to the generator breaker now, since SF6 is being banned, so obviously vacuum breakers would find their feet in the generator breaker applications also. And there are a lot of developments are required. Developments are being done. I've seen prototypes, or at least models which are claimed to have interruption capabilities of say 100 kiloampere, 120 kiloampere, 80% DC components. So such figures I have read. So work is happening in this field also, and we would definitely see vacuum breakers and generator breaker applications in the coming years. One interesting application which can come up is DC braking.
Hmm.
DC braking is in vogue. We have been talking about since a long time, but still DC breakers are not that coexistent with AC breakers, because, as per my knowledge, even today DC braking happens on the AC side. If there is an HVDC line, there are converter stations.
Yeah.
So we have point-to-point lines which are called links, HVDC links. And I may be wrong, but as per my knowledge, even today the interruption happens on the AC side. So if there's a fault, the AC side interrupters or AC side breakers trip, or there is some management in the power electronics which converts the AC to DC. But in future, if we talk about MVDC, then there'll not be just point-to-point lines. There will be multimodal networks. So even it will be kind of a grid, or a ring or a radial distribution may happen in future. And in those times, you would definitely need breakers which can interrupt DC. And DC breakers will not be a complete mechanical breakers. As I understand, they'll be hybrid. There will be some power electronics and some mechanical devices like vacuum breakers. So there's a lot of research being done to assess the feasibility of vacuum breakers. And there are prototypes, as we talk, there are prototypes. There are even applications which are on the field as pilots, which are testing the vacuum breakers for DC applications. So this is another interesting technology which will be coming up, vacuum breakers for DC applications. One more thing which will be happening is railway electrification.
Yeah.
In India, railway electrification is happening at a rapid pace. When we say electrification, the locomotives will be having vacuum breakers, which are installed on top of them. So a lot of new requirements for vacuum breakers would be coming up as we go ahead in railway electrification. And there are a lot of other applications which might come up, like why not vacuum interrupters in low voltage? Considering vacuum interrupters have so many advantage of, say, life, smaller size, low maintenance, then why not at low voltage applications if you can find some? To give you an example, the product called vacuum contactor, right?
Yeah.
So vacuum contactor, the life is quoted in terms of millions. It's not quoted in terms of thousands or so. It's quoted in terms of millions. So there are
Million
low voltage
operations, you're saying?
operations, yeah. Life in terms of operations, yeah. Not in terms of years, but in terms of operations. So definitely there will be more applications in low voltage domain also, considering the various advantage of the vacuum switching medium. Then other applications like capacitor switching, inductor switching. So these are also getting more and more into vacuum from the other type of switches. So my message to the young engineers is welcome on board. There are a lot of opportunities in the field of design, development, research, both fundamental research and application research, in the field of vacuum interrupters and vacuum breakers. As Gaurav mentioned and we discussed, there will be links in this video about various avenues where you can look up for the material related to vacuum interrupters. So read those materials, and if you are interested, definitely you can think about having or making a very good career in this field of vacuum interrupters and vacuum interruption.
Yeah, yeah. So very detailed breakdown shared by sir. What are the technologies that is coming? What is the future that you can expect? I will just summarize it in a very short statement that the future is bright. So, and especially in today's world where all the young engineers are, attracted towards the IT field, I would personally encourage you also look at this opportunity. Certainly, there are a lot of rewards also involved in this, and the satisfaction that you get out of this is, not comparable. So for sure, look at this opportunity also as a career option, and definitely it will reward you. Sandeep sir, thank you so much for your time. I think the discussion was really, really great. I personally learned a lot of things. For sure, there are a lot of things that we can learn from you. But thank you so much for your time, and I really appreciate that you came on board and share this precise knowledge with all of us. Thank you so much for your time.
Thanks, Gaurav. And even I have learned because every time I read a paper or read a book, I'm sure I learn at least one thing which is new, which I did not know yesterday. So through this discussion, even I learned quite a lot, and it was a very fruitful discussion. And I'm always happy to share my little knowledge on vacuum interrupters and attract people to this field. That's my selfish motive, I can say, to attract more and more bright engineers, young engineers to this field of vacuum interrupters. So thanks, Gaurav, for having me, and all the best to your videos and your initiative, I should say, for disseminating the knowledge on electrical engineering far and wide. And I'm very happy that your videos are getting a lot of views, a lot of likes, and world over they are being watched. So keep it up, and all the very best for this noble initiative.
Thank you, thank you, thank you so much, sir. I think the pleasure is all mine to have you on board. And if you have any questions for sir, you can just put it in the comment section below. We'll look at it and we'll try to answer them as well. So thank you so much, and we'll see you in our next video. Thank you. So that's the end of the part 3 of the discussion I had with Mr. Sandeep Kulkarni. I hope you enjoyed the discussion and have also learned a lot of things from this. And in part 3, we talked about the challenges the vacuum interruption had, or still it's going on. The research is going on that. And we also discuss the key opportunities, and from that discussion it is very much clear that the future is bright. There are a lot of opportunities that are going to come in terms of the vacuum interruption technology. So definitely, if you are interested, learn more about it. You can put your doubts in the comment section and we'll try to answer those for you. If you like this complete discussion, then do comment helpful. If you have any questions, feel free to put that in the comment section also. And do like this video if you found the whole series helpful. In the next episode, we have another expert with us, in which we are talking about the switchgear monitoring system in the medium voltage industry, which is, by the way, one of the hot topics in the industry. We are going to discuss on that part. And for that, you have to subscribe to the channel, because that's how you will be getting the updates. So thank you so much for watching, guys. I'll see you in the next one. But till then, keep watching, keep learning.